Lesson 4.6, situations that always or never happen. Our learning target is that we should be able to identify if a linear sentence, including both equations and inequalities, has one solution, no solution, or all real number solutions based on the algebraic solving. For a moment today, just a reminder of our linear situations. If you would please write an equation that represents the salary after Y years for each of the following jobs. Hopefully you came up with something that looks like this. In order to identify between job 1 and job 2, I have just labeled as S1, S2. You'll notice that the number is lower than the letter S. It is not an exponent, it's a title. It's called a subscript, which would be a title for S. Let's talk about when a situation has one solution. Most linear sentences have one solution that can be found either on a table, on a graph, or algebraically. Today we're actually going to take a look at a couple representations on a table, on a graph, and algebraically as well, but we're going to concentrate on when a situation has either no solutions or all real numbers as a solution. Never true or always true. So let's start out with sentences that are never true, where there is no solution. We're going to go back to our job situation with job 1 and job 2. We've got our equation that represents a salary for job 1 and our equation that represents a salary for job 2. It looks like our y's have been replaced with x's. No big deal. We'll just go ahead and use our x. It says we're going to add a question to the situation now. It says, after how many years will job 1 and job 2 have the same salary? So taking a look at what we just saw on a graph, on a table, algebraically, let's take a look at a table of this situation. If we have years worked, here they're representing it with an N, so we can interchange our variable as long as we are labeling carefully. Job 1, after 0 years worked, would be $30,000, and then after 1 year work would be $35,000, and after 2 years worked we can see $40,000. Job 2 here, we can see very similarly, after 0 years, $28,000, after 1 year, $33,000. If we follow this graph, each of these job salaries is going up by the same amount. They're always $2,000 apart. They're not getting any closer together. They're always $2,000 apart. And since they each go up by $5,000 each year, they're never going to be the same. So we cannot answer this question, after how many years will job 1 and job 2 have the same salary, because they never will. If we were to represent these situations on a graph, we can see job 1 here represented with blue dots and a blue line, job 2 represented with red dots and a red line. These two lines are going up by $5,000 at the same time. They're actually parallel lines. They're going up by the same, so the lines are parallel. They're never going to cross. The intersection point would be where job 1 and job 2 have the same salary, but there is no intersection point. Therefore, both on the table and on the graph, we can see that there is no solution to the situation. It's never true that job 1 and job 2 have the same salary. If we wanted to represent this algebraically, one thing to remember is when solving a sentence, if you get a sentence that is never true, then the original sentence is never true and has no solution. So in this particular instance, we're talking about the situation where job 1, salary 1, is equal to job 2, salary 2. We put this algebraically, 3,000 plus 5,000 y. Ooh, it looks like we've switched back to y for years again. I'm so sorry about that. There we go, take care of that. We can see salary 1 is still represented by 30,000, the starting salary, plus 5,000x, $5,000 per year, is equal to salary 2, which is represented by $28,000 starting salary, plus 5,000x, $5,000 for each year. We would solve this like we would normally do, eliminate the variable from one of the sides by adding the opposite of the variable term to both sides. Let's go ahead and eliminate this 5,000x by adding negative 5,000x to both sides. The resulting quantity here says 3,000 equals 28,000, or excuse me, 30,000 equals 28,000. This is not true. 30,000 is not equal to 28,000. Therefore, there is no solution for x, and this will never happen. We actually saw that this would never happen, that salary 1 would be equal to salary 2, as we took a look at our graphs. We saw that salary 1 would not be equal to salary 2 at any point in time just by looking at the table and the graph. They're never going to be equal. So again, algebraically, when solving a sentence, if you get a sentence that is never true, then the original sentence is never true and has no solution. In this case, x has no solution because there is no x where 30,000 plus 5,000x equals 28,000 plus 5,000x. Let's take a look at what happens when there's a sentence that is always true. So again, going back to our job 1 and job 2, starting salaries, 30,000, 28,000, and a yearly raise, both of $5,000. What about after how many years will job 1 have a higher salary than job 2? So algebraically, when solving a sentence, if you get a sentence that is always true, then the original sentence is always true and the solution is all real numbers. So algebraically, let's write this in words. We want salary 1 to be greater than salary 2. So job 1 has a higher salary than job 2. Now we're going to write it algebraically. So we want 30,000 plus 5,000x to be greater than 28,000 plus 5,000x. Greater than 28,000 plus 5,000x. We want to eliminate the variable from one side by adding the opposite of the variable term to both sides. So let's go ahead and add the opposite of this term to both sides. Negative 5,000x added to both sides. And we arrive at the inequality 30,000 is greater than 28,000, which we know is always true. Therefore, the solution for x is all real numbers, and job 1 will always have a higher salary. This is what this looks like when we're taking a look at kind of a real life scenario. We're also going to examine today just kind of a generic equation, what happens when we're looking at a generic equation. So I'm going to ask that we solve the equation 7x minus 10 minus 3x equals 2 times the quantity 2x minus 4. So let's go ahead and get started. This, first of all, is super complex. Let's simplify anywhere where we can with like terms and using the distributive property. If we go ahead and do that, 7x and the negative 3x become 4x, so we've got 4x plus negative 10. Distributing the 2 times, we arrive at 4x plus negative 8 on the right side. We're going to need to add the opposite of one of these two terms here, so let's go ahead and add the opposite of negative 4x in order to eliminate. So the opposite of 4x is negative 4x, and we arrive at the equation negative 10 equals negative 8. Wait a second, that's not right. This is never true. Negative 10 is never equal to negative 8. Therefore, this equation has no solution. This equation has no solution. And if we want to write that, we often write x equals the null set. This is a common notation for no solution. Let's take a look at another, just a generic equation example. Let's go ahead and solve the inequality. 7q plus 1 is greater than 60q minus 4 minus 53q. Again, pretty complex looking. Let's combine like terms where we can. We arrive at 7q plus 1 is greater than 7q plus negative 4. Here we've combined the 60q and the negative 53q. We'll need to eliminate the variable term from one of the two sides by adding the opposite of the term. Let's eliminate this 7q by adding negative 7q to both sides. If we follow through simplifying like terms, we find out that 1 is greater than negative 4. Now this is something that we always know is true. 1 is always greater than negative 4. Our variable has disappeared. Therefore, this inequality is true for any real number. And we would say q is equal to all real numbers. This is a common way to write this. And that's it for today's notes.